Welcome to the video for 18.1, where we talk about rates of reaction. So before we watch this, you need to go back and just recap your previous knowledge from AS Kinetics. So you need to have a look at collision theory and the different factors that affect the rate of reaction, like catalysts, temperature, surface area, pressure, etc. Also Maxwell-Boltzmann distribution curves, and lastly, how catalysts work. So our learning objectives for today are: we need to be able to define the rate of reaction, describe experimental methods to follow reaction progress, and be able to determine the rate of reaction from a graph. So first of all, our rate definition. So the rate of reaction is a term that we kind of use without really thinking about it, but if you want the official definitions, the rate of reaction is the change in concentration of reactants or products per unit time. So it's how much product has been made in a certain amount of time, or how much reactant has been used up in a certain amount of time. So how do we measure rate? So if we think back to GCSE, you'll have done some various experiments where you've measured the rate of reaction. So you might have measured the volume of gas evolved. So there's a picture there of a gas syringe, which is the best method for collecting gas and measuring the volume of gas given off in a reaction, but you might have done it in an upturned measuring cylinder in a trough of water by displacement. You can also measure, if you've got a gas being given off, you can measure the mass change on a mass balance. That works better for high density gases such as carbon dioxide. If you use it for something like hydrogen, which is low density, then you won't get a very big change on the mass balance. And the other one that you might have done at GCSE is the time taken for a precipitate to form. So if you do the reaction of biosulfate, where you produce the sulfur precipitate, then you find that what happens, so if you put a paper with marks of a cross on underneath your conical flask, which initially you can see because the initial reaction mixture is transparent. And then over time, the sulfur precipitate forms, and that obscures the cross and you can't see it anymore. So you measure the time taken from the initial mixing of the reactants to not being able to see the cross because it's obscured by the precipitate. So at A level, we can add a bit more sophistication here. So in your required practicals, you'll look at something called the iodine clock, where you'll get a drastic color change. And also, if you have a color change, you can use a colorimeter to measure the light intensity. Now, we won't do this in a school classroom, but you could do it in a normal university laboratory. And it's something that we'll talk about that you could be examined on. So by the colorimeter is just a machine that measures the light intensity at different wavelengths. And that light intensity is then proportional to the concentration of that reactant or product. So how do we calculate the rate from these methods? So for things like a color change, where you get a sudden color change, like the iodine clock, or if we've got a biosulfate reaction where you produce a precipitate which obscures a cross, then the 1 divided by the time will give us a value proportional to the rate. So you can't measure the rate at different points in the reaction, you're just getting a value for the overall rate of reaction. If we've measured the gas volume or mass changes, or we've directly measured the concentrations of the reactants or products, then we can get a more nuance here, because we can get, as well as working out the overall rate, we can measure the rate at different points of the reaction. So we do this by plotting a graph of either the gas volume or the concentration on the y-axis, and you have time on the x-axis, and that's going to produce a curve which will eventually level off, and it levels off so that line becomes horizontal when the reaction is finished, because there's no longer a change in the concentration of the reactants or the products. And by measuring the gradient at various points on that graph, you can measure the rate at different points. Now you'll see on that graph that it starts off really steep and it gets gradually less steep. So the gradient or the rate is high at the start, and then it gets lower until it eventually stops. And that's because of the concentration of reactants. So as we know, the concentration of the reactants affects the rate of reaction. So the higher the concentration you've got, the higher the rate of reaction. So when you first mix those reactants, you're going to get a high rate of reaction. As those reagents are used up, then you've got a lower concentration of reactants, so the rate of reaction will slow down, which is why we get this curve. So from this curve, if we want to work out the gradient, if we want to work out the rate, we need to work out the gradient. So to work out the gradient of a curve, we take any time along that curve and we draw a tangent. So we draw a tangent at whatever point it is, whatever time it is we want to measure the rate, and we then work out the gradient of that tangent by dividing the change in y by the change in x, and that gradient will be equal to the rate. And the units of that will depend on what we've measured. So in this case, we've got concentration against time, so it will be moles per decimeter cubed per second. If we had a gas volume measured in centimeters cubed, then it will be centimeters cubed per second. So we need to be able to interpret these rate graphs. So as I've said, the steeper the gradient, the faster the reaction. So as you do things to affect the rate of reaction, that gradient will change. Also important is the final height of the line. So the final height of the line is a measure of how much product has been made, and that's going to depend on the number of moles of the limiting reactant. So if you change the number of moles of the limiting reactant, you'll change the height of the final curve. So as an example, here's our original line was in black. So let's assume we've got the same amount of limiting reactants. So you're going to get the same final height on the curve. So the line in green shows that we've got the same final height of the curve, but you've got a faster rate of reaction because we've got a steeper gradient. So that would happen if we had a higher temperature. It would happen if we had a larger surface area, so we had smaller lumps or powder if it was a solid. If we added a catalyst, we'd get a faster rate of reaction. And if we had a higher concentration of reactants, we'd get a faster rate of reaction. The red line shows what would happen if we had a slower rate of reaction, so that might be a lower temperature. Apologies, I've just seen the typo on that. It should, of course, have an E between the P and the R. We'd also have a slower rate if we had a smaller surface area, so we had larger lumps if we had a solid reactant, and if we had a lower concentration of reactants. So this is what would happen if we had a change in the number of limiting reactants. So the red line again shows a faster rate, so we might have a higher temperature, a higher concentration, etc. But in that case, we've also got more of the limiting reactant. So if we put more of the limiting reactant in, we're going to get more product. So the final height is going to be higher. And in fact, that hasn't actually leveled off yet at that point. The green line shows a slower rate, but it also shows that we've got less of the limiting reactant, so less product is made. Normally, when you get an exam question on this, they'll make it that you've got either half or twice or something easy so that you can get the height exactly in the right place. So here's an example question that I want you to pause the video and have a go at. So it gives you the concentration, volume, temperature, and the sorry, that says catalyst, but it shouldn't be. That should. Oh, sorry, yes, it is. So it's the surface area of the catalyst. It's got various figures for the concentration, the volume, and the temperature. And the graph that's plotted there is for experiment 1. So what you need to do is draw 2 lines on the graph to show how the volume of oxygen is going to be collected. So what the final volume of oxygen is going to be in comparison to 1 and how steep that gradient is. So pause the video, have a go at that, and then the answers on the next slide. So we should have had for line 2, we should have had that steeper than the original and finish at the same height, because if we look at that, so it finishes the same height because we're comparing 1 and 2, the concentration of volume is the same, so the number of moles of oxygen is going to be the same, the temperature is the same, but the catalyst is in a powder, so it's going to be more effective. So you're going to get a faster rate of reaction. So the gradient is going to be steeper. And for number 3, the catalyst is the same, the temperature is the same, the volume is the same. What's different in that case is the concentration. So the concentration is half. So that means you're going to get a lower rate of reaction, so the reaction is going to be less steep. But because the concentration is half and the volume is the same, you're going to get half the amount of products. So the line is less steep than the original and finishes at half the height. Okay, that's all you need to know. Thank you for listening. See you next time.